Good morning, everyone. Yes, I'm Ben, and together with the amazing people at the Neuro TMA lab in Bern, we've been working on efficient learning of sequences in structured recurrent neural networks. Now, recurrent neural networks are great for learning sequences because they contain memory of past states in their dynamics. Unfortunately, learning in recurrent neural networks is very challenging, which is why one approach which showed promise early on was to not learn the recurrent connectivity at all, but rather restrict learning to the connections from the recurrent to an output layer. Unfortunately, this does not scale to more complex problems, so it seems like recurrent learning is needed. And here the state of the art is using the backpropagation algorithm. Unfortunately, learning with backprop through time uses quantity which are non-local in space and time, which is not biologically plausible. And while there have been some approaches which have tried to tackle this non-locality, these also suffer, for example, from very fast weight dynamics in the case of force, or from using global error signals in the case of follow. So in our approach, we adopted a key insight from biology, which was also mentioned yesterday by Emre, which is that the brain does not start from a randomized tabula rasa, but it contains some structural priors which allow to learn very efficiently. And here we introduce a structure in two key ways. So here you see our network. It contains a visible and a latent population. And the only difference between these is that the visible population receives a teaching signal. And what we do is we introduce structure by algorithmically generating a sparse and fixed scaffold of somato-somatic connections. And these pass the teaching signal from the visible into the latent population in a structured way. On top of this, we have a dense matrix of somatodendritic connections, and these are learned. All connections in our model are associated with delays. Now, the second way in which we introduce structure is in our neurons. So our neurons have an apical compartment, and the apical compartment integrates information from the network in a current-based way. And we have a somatic compartment, which is conductively coupled to the apical compartment, and it integrates the information from the teaching scaffold. Our neurons are unfortunately rate-based, and the rate is a nonlinear function of the voltage. And the reason why we have structure in our neurons is to allow them to represent all of the quantities that are necessary for learning. So here learning is, in learning, the dendrite targeting synapses are changed such that the network drives the neuron onto the target that is presented at the soma. That is our model. And now let's teach it to play some sequences. So here we teach our model, maybe you recognize it, to play für ELiSe by repeatedly showing the pattern. And we interleave pattern presentations with periods where we remove the teacher and allow the network to replay freely. Initially, the activity in the latent population simply dies out because the connections are not strong enough. But as learning progresses, the activity becomes more and more stable until finally we can remove the teacher and the network continues with replaying. This works across a wide range of parameterizations, including at more biologically plausible sparsities. Now we can show that the attractor that we entrain is quite strong by actually disrupting the output in the visible population by either clamping it to a very high or a very low firing rate. And when we let go, the attractor in the network again drives the output neurons towards the previously entrained pattern. That's it. If I've piqued your interest, then please feel free to check out our preprint. Or, more interestingly, we are going to host a Capo-Caccia workshop on ELiSe, and this will be hosted by the wonderful Timo Gerlich. Thank you very much.